Okay, so we just converted the um, the apparent angular speed from milliarc seconds, 0.8 milliarc seconds per year, to radians, 3.9 times 10 to the minus 9 radians per year. And now, if we realize that in 1 year the quasar will actually trace out precisely this number of radians. Okay, so in 1 year it'll go 3.9 times 10 to the minus 9 radians. Okay, and if we also, so then since tangent of theta is equal to little d over big D, and since this is an incredibly small number, okay, so tangent of theta is an incredibly small angle, then we can just approximate this very accurately with theta. So the distance, this distance moved in 1 year, little d, is equal to the angle theta times big D. If we plug in the numbers, what we get is that the apparent transverse motion of this quasar in 1 year is 10 light years. So the apparent speed is 10 light years per year. The apparent transverse speed is 10 light years per year. So incredibly, the quasar seems to be going 10 times the speed of light, and this is very strange, right? Because the maximum speed, relative speed between two objects is 2 times the speed of light, and that would be if they're both moving at speed c in opposite directions. Okay, and this is certainly not the case here. It's actually moving tangentially. So what the heck is going on here? Okay, so this effect is actually related to the Doppler shift that we discussed earlier in this lecture. So now let's imagine that this quasar is flashing with a period TE as measured in the Earth frame. That is, that this is the Doppler shifted. This is not the Doppler shifted. This is the Lorentz, or the time dilated period that of emissions, of flash emissions, as measured by the Earth observer. Okay, so the time between the reception of consecutive pulses, as we discussed when we derived the Doppler shift, is just this period. Okay, this time dilated period. Here I'm not putting in the explicitly the time dilation, because as we'll see, it doesn't matter, it drops out. But this is the time. This is the time dilated flashing period plus the extra time that's related to the motion of the quasar along the line of sight of the between the Earth and the quasar. Okay, and so we just get this expression here, and we've seen this before again in when we were deriving the Doppler shift, if you go back. Okay, now, but in the time between flashes, as measured in the Earth frame, in TE, the object moves transversely. In addition to radially, the object moves transversely, and it moves transversely by distance delta y is equal to that time times the y component of the velocity, v sine theta. Okay, and this can be rewritten as beta c times TE sine theta. Okay, so now the apparent tangential velocity, okay, is just simply delta y divided by delta t sub e. Okay, and if you calculate that, that's beta sine theta divided by 1 plus beta cosine theta times c. And if you look at this, when theta is very close to pi, that is when the velocity is very close to almost heading directly towards Earth, but with a small transverse component, then cosine theta is close to 1. And if beta is close to 1, so very high speeds, then cosine theta is close to minus 1, and this is close to 1 plus negative 1, which is very close to 0. And this numerator gets small, and the fraction gets very large, can be much larger than c. So in this case, you can have apparent superluminal velocities.